So let's talk about semi-supervised learning. Semi-supervised learning is one of the most challenges of Google and I can say almost all AI companies because you have billions of data. Your data could be images. If you are working in a natural language processing, your data could be text. If you are working in finance, your data is financial data. I mean, all asset classes, all of the assets, hundreds of thousands of assets. So if, for example, you're working in Google, you have billions of images. So billions of images. So just a few of them are labeled, maybe 2%, and 98% is unlabeled. Even our eyes, even humans, even animals, even a child, how they learn is about semi-supervised learning, because most of our data that our eyes receive is unlabeled, and we try to make some association, some kind of relation to other known and labeled information that we have in our mind. So you see, even humans are in their mind are trying to. I mean, their mind is designed in such a way to utilize semi-supervised learning. So the old idea is the nearest neighbor classifier. For example, you have lots of data, and you want to, for example, use nearest neighbor. For example, you have some other data as well. Your nearest neighbor classifier may say that, all right, so I just want to pick the nearest neighbors. I don't care about your density. I don't care about the distribution of data. So I only take this one. So this is one class. And the other one this is another class because it's the most nearest neighbors. But in reality, you should, if you use, so the problem of a nearest neighbor classifier is that it doesn't respect density of data. But, if you use a modern semi-supervised learning algorithm, then it's quite obvious that it should at least find these data and say that this is one group and these are another group. So it respects the density now. So classification function F, we call it F, should be smooth with respect to data density in order to observe these regions that are similar to each other. One of the most successful approaches is using graph. G is equal to V and E. And, these are vertices, your data points, and edges clearly show the affinity matrix W, how close two different data, two different images are. And you know that I've talked about graph Laplacian in my previous talks, that L is equal to I minus D WD minus. So, and dii is just the sum. It's a row sum. And so graph Laplacian defines a smoothness operator measured by F transpose LF, which is equal to IJ. I will explain this, what I mean by minimizing this objective function and why should we minimize this objective function that we see in all the articles. Uh, I mean, if two points have great affinity or similarity, then they should have. So this clearly should be should demonstrates how we should penalize different terms. And so, of course, this is a trivial solution, and this has a trivial solution. But if we add the labeled or supervised section of that, then it becomes a non-trivial solution. So how can we make it non-trivial? By just finding a label function that minimizes F transpose LF plus your classical traditional supervised learning, which you just have label for your data. So this is the agreement with labels. And of course, this lambda is your weight, and we have very, very few labels. And so we can rewrite this objective function as in the matrix notation F transpose LF plus F minus Y transpose lambda F minus Y. And if you just take derivative with respect to F, you will have this nice solution, because you know that L plus F is lambda Y, and so you just need to invert this billion by billion matrix. Can you imagine that? So it's not practical, because this matrix, you should be realistic of your algorithm, because it is now billion by billion matrix. So let's just project it and say in your bases, which are phi1 through phi k, and these are the smallest eigenvectors of L. So I have done a kind of reduction, for example, in representation theorem in kernel learning, you try to represent it with sum of alpha I k. Do you remember that you try to reduce the infinite dimensional space of functions to just a finite dimensional, for example n alpha, and then so we do the same trick here, but we just use the space of eigenvectors and we kind of project it to this space. So now the problem is hugely reduced to just a finite dimensional space, and the cost function is dependent on finite parameters plus U alpha minus Y transpose alpha U alpha minus 1, U alpha minus Y. So the diagonal matrix, this is the diagonal matrix of eigenvectors of graph Laplacian. So optimal alpha is now the solution to K by K system. So sigma plus U transpose alpha U. So I can write it as sigma plus U transpose alpha U lambda U alpha is equal to U transpose lambda Y. And this is a K by K matrix. I mean, K is the number of this is the number of eigenfunctions, eigenvectors. Here we are dealing with matrices. So So, but the problem is still remains, because how do we find eigenvectors if n is huge? And so we have changed the problem of diagonalizing 80 million to 80 million matrix and finding eigenvectors of L. So a trick by Nystrom to deal with these kind of complexities is that just pick small set of points. This is one extreme, because you can go in another extreme. I will talk about it in a bit. But in this approach, you compute exact solution on these small set of points, and then interpolate, and then you interpolate solution to the rest. Another extreme is to, the back and forth between continuous and discontinuous domain is that you use the smoothness operator LP of F. Of course, I'm not a fan of this approach because of many problems, and because the separability assumption in this approach is too strong. Although many people are excited about this approach, but I'm not excited, because in reality you cannot use such strong assumptions. So f of x1, f of x2, w x1 and x2, and for example, they assume that px1 and px2 is separable, which I said you cannot do it in practice. And this is your typical weight, which is as usual, 2 epsilon. And so this is the continuous analog to graph Laplacian. We try to analyze the eigenfunctions of the LP of F. So analytical forms of eigenfunctions exist only in few cases. Uniform, Gaussian, and not all cases. So instead, they try to use a numerical approximation to eigenfunctions, and then going back to discrete case, going back to continuous case, going back. So this loop, their algorithm is that first they do PCA to make it more separable. It's a bad assumption that they can do that. They can never do this in practice. And so after that, they construct 1D histogram to solve it numerically for eigenfunctions. And then they order their eigenfunctions, and finally interpolate data into k eigenfunctions. This yields approximate eigenvectors in normalized Laplacian. And finally, in step 5, they solve their k by k least square system to give label functions. Now, I want to talk about spectral graph theory, because many of the results of semi-supervised learning is based on spectral graph theory, and also I will talk about graph limits, which is graph limits, and how I defined how I relate it to recent results. Of course, it is published in mathematical journals. It is not yet published in AI or machine learning journals. because mathematics is always ahead of time. So they are seeing the future, then they live in future. But machine learning still is walking very, very slowly. So let's talk about spectral graph theory. I mean, just the intuition behind that. And in the next lecture, very briefly, I will talk about details. So spectral graph theory, we have graph G and we have vertices and edges. You can imagine you have heat on nodes. This is a great way for intuition. So we want to, it's like discretizing heat. You know, heat, it can be a vector un for all of your n vertices. I mean, you have 1, 2, and n vertices. And for example, if your d is 5, I mean degree, it means that this heat node propagates the heat 1, 2, 3, 4, 5. So it propagates. So it's like a heat equation, and then it propagates further, and so it distributes heat to very cold places. So in practice, these red regions, red nodes, are very rare and they are labeled. So it's like it's a random walk matrix, and your W matrix is acting on this vector of heat. So the ith coordinate is the first average on itself, and then average of its neighbors. So this is the intuition behind that. Inside edge and uj. So you see that wii is 1, wij is 1 to this degree, and if inj is an edge, and otherwise, well, it is 0. Otherwise, it is 0. So you see that w is real and symmetric. And so we can write W is equal to I from 1 to n, W1 I UI, I from 1 to n, W2 UI, I from 1 to n, Wn and I, Ui, and you kind of do it again in a higher order, do it again, so it becomes and this I and j from 1 to n, WNJ, WJ, I, UI. So let's diagonalize W, since we use it again and again. So why not diagonalizing and make it more simple? So because W is symmetric matrix, and so we are lucky that eigenvalues are real because W is symmetric. So mu1, mu2, mu-n, these are real. And eigenvectors are v1, v2, vn. So we can write, for example, your heat as, so in this new basis, which is space of eigenvectors, you do it in linear algebra, if you remember, and you represent it in this new space. And now everything is crystal and easy. So I'll